Hello students, this is Professor Chalai, and in this video we're going to go over some information about density. Specifically, we're going to learn about how to find the density of regularly and irregularly shaped objects. We're going to use graphical analysis to find density from experimental data, and we're going to predict masses or volume from values of density. So let's get started. So what is density? By now we all know that density is a measure of the mass of an object divided by the volume of an object. And in chemistry, we typically measure that mass in, for example, grams, and volume in centimeters cubed or milliliters, and their equivalent. So this means that for density, we would find measurements that have units, has units of either grams per centimeter cube or grams per milliliters. Again, those mean the same thing. So if we wanted to find the density of an object, all we had to do was go ahead and find the mass of that object, find the volume of that object, divide the two, and we get the density. So let's look at that. Let's look at regularly shaped objects. And a common regularly shaped object is, for example, a cube, right? Something like this, or any cuboid shape with some length, width, and height. Or spheres. Spheres are common objects too, right? With some radius. And the volume of that cube is simply just the length by the width by the height. The volume of a sphere, if you remember, is just 4/3 pi r cubed. For these sorts of regularly shaped objects, all we have to do is go about finding the mass, finding the volume, and divide the two for the density. Similarly, for something like a sphere, we can find the diameter and divide it by 2 to get the radius, and from that we can find the volume, and then we just take the mass divided by the volume to get the density. But what about irregularly shaped objects? So let's look at that. Irregularly shaped objects. These are objects where you can't easily find the volume of. Let's say it's a shape like this, right? Who knows how big that is? There's no easy way to find the volume of this by measuring the dimensions of this object. So how can we go about finding the density? Well, it's easy to get the mass, right? You just put it on a scale, you can get the mass. But the volume, what is the volume equal to? Well, an easy way to find the volume is to take a measuring cylinder, right? So let's say this is our measuring cylinder, and we fill it up with some amount of water to some level. Not all the way up, just enough in there. Then we can put our irregularly shaped object, and obviously what's going to happen is that water level is going to rise. If we take the starting volume, let's say the starting volume was 13.32 milliliters and the ending volume was 20.56 milliliters, then this difference here is the volume of our object. So in this case, the volume would simply be the final volume, 20.56 minus 13.32 milliliters. And so if I can do some quick math here, I think that's 7.24 milliliters as a volume. So in a case like this, it's easy to get the mass. We can calculate the volume using this method in our in our measuring cylinder. And this is the technique that we're going to use in lab. We're going to be trying to find the density of some irregularly shaped objects, and we're going to find the volume using this measuring cylinder method. Now, a quick point to note, these measuring cylinders are typically made of glass, so you might see a little rubber stopper at the bottom here. That doesn't change any of the results. You just pour your water in here, make sure there's enough in there, then add your volume. You want to make sure that you measure where you start off first. Then you add your object, and then you measure how far up it rises. Alright, so that's how we measure density for regularly shaped and irregularly shaped objects. But in science, we don't take one measurement. We don't take one mass and one volume and find the density once, right? You want to be sure, so you might do this many different times for many different sizes of objects with different masses and volumes. And so to really analyze that data, we're going to use a graph. So let's look at this again. We said density is mass over volume. So right away we should be thinking it's relating to quantities. What else relates to quantities? Well, a slope of a line could. So if we want to relate the density to the slope, we know slope is the same as rise over run, right? So if we're going to create a graph with our data, the mass should be the rise of our graph, or the y-axis, and the volume should be the run, or the x-axis. And that's how we'll create a graph. So you will plot all of your data, you'll get your best fit straight line, y is equal to mx plus b. The m here that your graph gives you, that is the slope, that is the density. They're the same thing. The units for that m will simply be the units for your mass. Typically that will be grams, over the units for volume, that will be milliliters. All right, and then finally what I want to talk about is, what if you want to go the reverse? What if you calculated the density for an object? Let's say you did this with steel, right? So you had pieces of steel, you found the mass, you found the volume for each one of them, and so then you plot your graph, here's mass, here's volume for all the pieces, and you made your best fit straight line, and m here will be the density, and you did all that for small pieces of steel. Is it steel that I said it was? Yeah, let's go with steel. And you found that the slope was 8.05 grams per milliliter, right? You can transform these units to other units, and it's 8050 kilograms per meter cube. They're just unit transformed. Usually we use this for steel just because, especially when we're talking about large pieces. Okay, so that's our density. What if you want to find out how much a piece of steel that is, let's say it's a block of steel, kind of like this, maybe. That's 1 meters on this side, 2 meters on this side, and maybe, let's say, 5 meters on that side, right? You want to figure out how much this block of steel weighs. Well, you could go out and buy a very, very large scale and try to find a mass of this block of steel. Or you could use the density. You know it's steel. You know the density. You can calculate the volume, right? It's a block, so it'll be 1 meter by 2 meters by 5 meters, which in this example gives me 10 meters cubed. So I know the volume and I know the density. So how can I find the mass? Well, let's look at the equation. Again, density is equal to mass over volume, right? If I multiply both sides by volume, then I get mass on the right-hand side is equal to volume times density, right? And I could use that equation to solve for the mass. So the density that I said earlier was 8,050, 8050 kilograms per meter cube. The volume I just calculated was 10 meters cubed, and so the mass that I end up getting, meters cubed cancel out, would be 80,500 kilograms. And of course that's super heavy. I don't think we have a scale that can measure that amount. Maybe we do, I don't know. But let's say instead of mass you wanted to find a volume. So density is mass over volume. We do the same trick. We multiply both sides by volume, right? Such that volume cancels out here. But then we also divide both sides by density. That way density cancels out here, and we end up with volume is equal to mass over density. And so these two are two equations that you might want to keep in your back pocket. Or you can figure it out just from the main starting equation to figure out either mass or volume starting with density. And that will bring us to the end of this video. I'll see you all in labs.